Well, we're now at a point where we can begin to start working some example problems, and let's start with really a pretty easy one, related to just what we've been talking about in this lecture. And here the problem statement is how much heat must be added to a system at 300 Kelvin for the number of accessible states to increase by a factor of 10 to the 100, which is a lot, right? Yeah. It's a huge increase. And the solution is pretty straightforward. You just have to realize that this is sort of a direct application of the Boltzmann entropy relation, which we just got through talking about. And that's the entropy is equal to K sub B, the Boltzmann constant, times the natural log of the accessible states. And I would write it probably as delta S, how much entropy is increased by this additional heat that's added into the system. And to me, delta of anything is the final minus the initial. In this case, the final is entropy at the final state 2, and the initial state was S1, entropy in it. And those are related simply by the number of accessible states at each one of those stages. So the entropy at stage 2, the final state, Kb natural log times the thermodynamic probability at the final state, and then minus S1 is minus Kb times the natural log of the thermodynamic probability, or the number of accessible states at the initial. And I can factor out the Kb and then sort of do what we've been doing in reverse. We've got a difference between logs, which is the log of a ratio. But we're given here that omega 2 is 10 to the 100th times omega 1. And so one just plugs that in for omega 2 up here. I've done it. And the omega 1s, the initial state, goes out. That's the nice thing about logarithms, is this sort of thing happens. And I get Kb times the natural log of 10 to the 100th is the change in entropy. And using again the property of logarithms, the natural log of 10 to 100 is 100 times the natural log of 10. Boltzmann constant is 1.38 times 10 to the minus 23. And when I worked that out on my calculator anyway, I got the change in entropy was 3.18 times 10 to the minus 21 joules per Kelvin. So pretty small amount for such a large number of increase in states, right? Now then, we need to relate that to the heat. They want to know how much heat was added, and oftentimes I'll just write this as delta S as delta Q over T, but really it's for a reversible heat transfer. And so I can solve this. The delta Q is T delta S, and I've just calculated delta S. So multiply that times the temperature it was added at, 300 Kelvin. And when I multiply those out, I get 9.53 times 10 to the minus 19 joules. And if you convert that to electron volts, you get approximately 6 electron volts. So that's the answer to our original question, which was how much heat must be added? Approximately 6 electron volts, or the equivalent number of joules, to increase the accessible state factor by 10 to the 100.